Welcome you in the lecture series of random processes detection and estimation. It is 41st lecture of this series. In the previous lecture we have discussed Bayesian estimation and mean square estimation. In this lecture we will discuss more about minimum mean square estimation and the Bayesian linear model. And the outline of this lecture are minimum mean square error estimator and properties of Bayesian estimator. In the objective of this lecture, you will be able to explain the concept of minimum mean square estimation and what is the linear model. Now we will start with the minimum mean square error estimator. You know, when the actual value or prior knowledge of theta could be factor, it means where the MVUE does not exist for a certain value or where prior knowledge would improve the estimator performance. The classical approach would not work efficiently there. And you know, in the Bayesian approach, the parameter theta to be estimated is treated as a random variable with a known prior PDF p theta. Such prior knowledge concerning the distribution of the estimator should provide better estimators than the deterministic case. In classical approach, the MVUE estimator is derived by first considering the minimization of the mean square error, that is theta MVUE cap will be the minimization of mean square error theta cap with theta. And you know, the MMSE theta, it is the expected value of the whole square theta cap minus theta, or you can say the integration whole square of theta cap minus theta into px theta dx, where px theta is the PDF of x parameterized by theta. In Bayesian approach, the estimator is similarly derived by minimizing the Bayesian mean square estimator, and it will be theta cap. It will be the minimization of Bayesian mean square estimation theta cap, and where this Bayesian mean square estimator theta cap, it will be the estimated value of the whole square of theta minus theta cap, or you can say the double integration theta minus theta cap whole square px theta dx d theta. It is the Bayesian mean square error, and px theta is the joint PDF of x and theta. You can see that the squared error theta minus theta cap whole square is identical in both Bayesian and classical MSE. The BMSE theta cap estimator or minimum mean square estimator is derived by differentiating the expression of this BMSE with respect to theta cap and setting it to 0. Then we will get theta MMSE cap. It will be the conditional expected value of theta given x, and you can write it as theta conditional PDF p theta by x d theta, where the prior PDF p theta by x is given as px by x theta by px, the joint PDF of x and theta, and it will be equal to px theta divided by integration px theta d theta. And this is marginal PDF of x, and you can find out the marginal PDF by integrating the joint PDF with respect to theta. You can find the marginal PDF of x here. So, and it will be equal to, from the Bayes theorem, it will be px by theta p theta divided by px by theta p theta d theta. Now consider one example. Consider a signal in presence of noise. Xn is equal to a plus omega n, where small n is from 0 to n minus 1, and omega n is the random process with mean 0 variance sigma square. The unknown parameter theta is equal to a is to be estimated. Let a is a random variable with prior PDF. Pa is the normal random variable with mean mu a and variance sigma a square. We also have the conditional PDF of x. Px by a is the Gaussian random process with mean a and variance sigma square, and a and x are jointly Gaussian here. So now the post prior PDF px by a, it will be px by a pa divided by px by a pa dA from the previous equation, and it will be approximately normal random process with mean mu a by x and variance sigma a by x square, and it is also Gaussian PDF. After some required simplification, we will have PA, it will be equal to 1 by under root 2 pi sigma a square into e is to the power minus 1 by 2 sigma a square and whole square of a minus mu a. Mu a is the mean value of a. And the conditional PDF Px by a, it will be 1 by under root 2 pi sigma square is to the power n by 2 into e is to the power minus 1 by 2 sigma square summation n0 to n minus 1 and whole square of xn minus a. And I can write it as 1 by 2 pi sigma square is to the power n by 2 into e is to the power minus 1 by 2 sigma square summation n0 to n minus 1 x square n and into e is to the power minus 1 by 2 sigma square and into n a square minus 2a n and sample mean x bar. And now the conditional PDF PA by x, it will be from the Bayes theorem, it will be Px by a PA and divided by Px by a PA dA and integration of this term, and you can find out it will be equal to in e is to the power minus 1 by 2 into 1 by sigma square into na square minus 2na x bar plus 1 by sigma a square and whole square of a minus mu a divided by integration e is to the power minus 1 by 2 into 1 by sigma square into na square minus 2na x bar plus 1 by sigma square and whole square of a minus mu a dA. Now from this we will get sigma a by x square, it will be equal to 1 by n by sigma square plus 1 by sigma a square, and the mean value mu a by x, it will be n by sigma square x bar plus mu a by sigma a square into sigma a by x square. So the minimum mean square error estimator of a, it will be a MMSE cap, it will be equal to the conditional expected value of a means e a by x, and it will be mu a by x, or it is equal to n by sigma square x cap plus mu a by sigma square divided by n by sigma square plus 1 by sigma a square. So the final MMSE, you can write it as sigma a square by sigma a square plus sigma square by n into x bar plus sigma square by n divided by sigma a square plus sigma square by n into mu a, and we can write it as alpha x bar plus 1 minus alpha mu a, where alpha is sigma a square by sigma square plus sigma square by n, and the conditional variance VA by x, it will be sigma a by x square, it is equal to 1 by n by sigma square plus n 1 by sigma a square, and the BMSE Bayesian mean square error a cap, it will be expected value of whole square of a minus a cap, you can write it as a double integration whole square of a minus a cap PA by x dA px dx, and since estimated value of a cap is, this is conditional expected value e a by x, then we have the Bayesian MSE of a cap, it will be integration variance a by x px dx, and it will be equal to 1 by n by sigma square plus 1 by sigma a square. Since sigma a by x square does not depend on x, so the BMSE a cap, it will be sigma square by n into sigma a square by sigma a square plus sigma square by n. So here you can see that BMSE a cap is less than sigma square by n, where sigma square by n is the MMSE obtained when no prior knowledge is available. Clearly, any prior knowledge when model is a Bayesian sense will improve the Bayesian estimator. Here sigma square by n is the MMSE obtained when no prior knowledge is available. Clearly any prior knowledge when modeled in Bayesian sense will improve the Bayesian estimation. Now we will discuss the properties of Bayesian estimator. The first property, Bayesian linear model. Consider the Bayesian linear model x is equal to h theta plus omega, where theta is unknown parameter to be estimated with prior PDF normal process with mean mu theta and covariance c theta, and omega is white Gaussian noise with PDF normal process with mean 0 and covariance matrix c omega. The MMSE is provided by the expression for the conditional expectation of y, means expected value of y by x, where y is equivalent to theta. So we have expected value of x, it will be h mu theta, and expected value of y is equal to mu theta. So the covariance of x, it will be cxx. It will be the expected value of x minus ex, and transpose of x minus ex means correlation of the centered random variables, and it will be equal to h c theta h transpose plus c omega, and cyx cross correlation, it will be expected value of y minus ey into x minus ex transpose, and it will be c theta h transpose. Since here x and theta are jointly Gaussian, then we have at theta cap, it will be a conditional expected value of theta e theta by x, and it is equal to mu theta plus c theta h transpose, and inverse of the matrix h c theta h transpose plus c omega into x minus h mu theta. Now another property is the new sense parameter. Suppose that both theta and alpha were unknown parameter, but we are only interested in theta. Then alpha is the new sense parameter. We can deal with this by interchanging alpha out of the way. Considering the Bayesian rule for the posterior PDF, p theta by x is px by theta p theta divided by integration px by theta p theta d theta. Here px by theta is px by theta with alpha, and so px by theta, it will be the integration px by theta alpha into p alpha by theta d alpha. So if alpha and theta are independent, then we can say that px by theta, it will be integral p x by theta alpha into p alpha, because it is independent from theta. So here p alpha d alpha. Now third property is the relation with classical estimation. In classical estimation, we don't make any assumption on the prior, so all possible theta have to be considered. The equivalent prior would be a flat distribution, and sigma theta square will be infinity. This is a non-informative prior PDF will gives the classical estimator. Now consider one example here. Consider the signal in presence of noise xn is equal to a plus omega n, where small n is from 0 to n minus 1. We already discussed that in the previous lecture that a cap is the alpha x bar plus 1 minus alpha mu, and where alpha is sigma a square divided by sigma square plus sigma square by n. If the prior is non-informative, then sigma square is infinity and alpha is 1. So here you have a cap minus x bar will be mu a, and it is classical estimator. So far in this lecture, we have discussed minimum mean square estimator and Bayesian linear model. This was 41st lecture of the lecture series of random processes, detection and estimation. In the next lecture, we will discuss about general Bayesian estimator. Till then, thanks for listening to this lecture. Thank you.